Alright, so today we're going to move on to section 3.4, and we're going to be talking about continuity and limits. We want to understand when something is continuous versus discontinuous and what types of discontinuities do we have. This is something that I know I've used the phrase continuity as we've been talking about limits so far already. For instance, polynomials are continuous everywhere. Rational functions are continuous everywhere except for wholes and vertical asymptotes. Things like that. So I gave you that handout that has basically all of the notes on it, so you're not going to be writing a ton for at least this first part, but pay attention, listen to my charming voice, and, you know, try to get something out of it. So here we have the pictures of three different ways in which, or three different conditions for which a function is not continuous. So the first is showing that the function is not defined at the point. So if f of c is not defined at c, then it is not continuous at c. If the limit of f of x as x goes to c does not exist at c, then the function is not continuous at c. If the limit exists, but it does not equal the function at c, then the function is not continuous at c. So one thing that I want to clarify, when we're talking about continuous, we're talking about continuous at a specific point in this case. So, you know, if I look back at this graph here, the function is continuous between a and c, and between c and b. It is just not continuous at c. So then this leads us to our definition of continuity at a point. A function is continuous at c if the following three conditions are met. F of c is defined, the limit as x goes to c of f of x exists, the limit as x goes to c of f of x equals f of c. So continuity on an open interval. A function is continuous on an open interval a to b if it is continuous at each point in the interval. A function that is continuous on the entire real line, negative infinity to infinity, is continuous everywhere, or is everywhere continuous. Alright, real quick, open and closed interval. So we should recognize the notation. So when we're talking about open interval, that's when we have parentheses a, comma b, parentheses. So what this means is it doesn't have any defined endpoints. It does not mean that it's all real numbers, though. A and b do not have to be negative infinity to infinity. So, you know, we can have this where this is at a and this is at b. Or a and b could be infinity or negative infinity. That's still an open interval. But basically whenever the endpoints are parentheses, that means that they're not included. We don't have defined endpoints. Closed interval then would be our brackets. So this is where we have defined endpoints. So here, you know, picture could look like this. That's a bad picture because this is not a function there, so let me make a quick adjustment. Good stuff. There we go. So that would be b. So that would be a closed interval. Okay. Definition of continuity on a closed interval. A function if f is continuous on a closed interval, a to b, if it is continuous on the open interval, a to b, and the limit as x goes to a from the right of f of x is f of a, and the limit as x goes to b from the left of f of x equals f of b. So notice that those are one-sided limits because the function does not have to exist beyond those. The function f is continuous from the right at a and continuous from the left at b. So again, there's a picture. So consider an open interval I that contains a real number c. If a function f is defined on I except possibly at c, and f is not continuous at c, then f is said to have a discontinuity at c. We have two types of discontinuities. We have removable and non-removable. Removable discontinuity is a discontinuity at c if it can be made continuous by appropriately defining or redefining f of c. So an example of a removable discontinuity is a hole. So think about when we factor out and then reduce the function to get rid of the hole, that's a removable discontinuity. A non-removable discontinuity is a discontinuity where f cannot be made continuous. So that would be like a vertical asymptote. There are other examples of removable and non-removable discontinuities. These are two that you should be able to picture pretty easily in your head. Properties of continuity. So if k is a real number and f and g are continuous at x equals c, then f plus g, f minus g, f times g, k times f, and f divided by g, assuming g of c does not equal 0, are also continuous. The following types of functions are continuous at every point within their domain: polynomial functions, rational functions, and radical functions. So those are all continuous at every point within their domain. So rational functions are not continuous everywhere, but that's because their domain is not all real numbers. Same with radical functions. Okay, so now on to some examples. So for the function at the right, I want you to find the limit as x goes to c from the right, as x goes to c from the left, and the limit as x goes to c. Determine is the function continuous at c, and then explain why or why not. And if it is not, is it a removable discontinuity? Pause the video, answer those, unpause when you're ready to check your work. Okay, so we can see the limit as x goes to c from the right. So that's, as I'm approaching c from the right, is -2. The limit as x goes to c from the left is -2. Therefore, the limit as x goes to c is going to be -2. So is the function continuous at c? Yes, it is. Not because of number 1. It's continuous because f of c is defined. I can see that -2 is a point on the graph. The limit exists at c, and the limit at c is the function value at c. So that is why it is continuous at c. Next, evaluate the limit as x goes to c from the right, c from the left, and c. Is it continuous at c? Why or why not? Is it a removable or non-removable discontinuity? Pause the video, unpause when you're ready to check your work. Alright, so here the limit as x goes to c from the right is 2. The limit as x goes to c from the left is 2. Therefore, the limit as x goes to c is 2. Is the function continuous at c? No, because the limit as x goes to c of f of x does not equal f of c. F of c is 3. Is this a removable discontinuity? Yes, it is. It is a removable discontinuity because f of c could be redefined to make it continuous. So I could redefine that point as -2, 2, then it would be continuous. Next one, for the function at the right, find the limit as x goes to c from the right, c from the left. C is the function continuous at c? Why or why not? If not, is it a removable discontinuity? Pause the video, unpause when you're ready to check your work. Alright, so here I can see the limit as x goes to c from the right is this. That's going to be 0. As x goes to c from the left is here. That's going to be 2. Therefore, the limit as x goes to c does not exist. The function is not continuous at c because the limit as x goes to c of f of x does not exist. This is not a removable discontinuity, though. Redefining f of c will not make it continuous at c. No, more things need to happen. Alright, next is f of x equals the absolute value of x, continuous at x equals 0. Prove it. Pause the video and pause when you're ready to check your work. So yes, it is continuous at x equals 0. We know that because f of c, so in this case f of 0, is 0, so it's defined there. The limit as x goes to 0 of the absolute value of x, or of f of x, is 0, so the limit exists. And the limit as x goes to 0 of f of x is the same as the function value. So the limit as x goes to 0 of f of 0 is f of 0. So all of our conditions are met, so therefore it is continuous. Last example. What value of a makes this function continuous? So pause the video, find that value, unpause when you're ready to check your work. Okay, so what I need to do here is, 1, recognize that at -1 the function does exist, so f of -1 is -1, and therefore in order for the function to be continuous, the other piece needs to be approaching -1, because I know that the limit from the right as x goes to -1 is -1. So the limit from the left also needs to be -1. So therefore I set this function equal to -1 when x is -1. Plug that in, solve, I get a equals -3. So -3 is the value that will make this function continuous. You could double check that by graphing it on your calculator if you would like, or you could trust your algebra. Alright, conclusion. A function is continuous at a value if it is defined at the value, the limit exists at the value, and the limit at the value is the same as the function at the value. Open interval means no defined endpoints, closed interval is defined endpoints. That was a fun lesson. See you tomorrow.